Hi, so this is the first class of the TA practice class, and as I already dealt with the discrete random variable in last week, for today's lecture, we're going to deal with the continuous random variable such as uniform distribution, normal distribution, as well as exponential distribution. So you can refer to this R file whose name is Ch4. And as you can see, we are dealing with three kinds of the R functions from three distribution, as I already mentioned. So it is not that different from what we did in the last week, as we deal with the discrete random variables. So as you can see, actually when we deal with the discrete random variable, we started with a D. So when you're dealing with for example, binomial distribution, there is a our inner function whose name is D binom and P binom, Q binom, R binom. So D function gives us the density value of the distribution, and P function gives us the CDF value of that distribution, and Q function gives us the quantitative value from that distribution, and as the last thing, R distribution, R function gives us the random sample from that distribution. So likewise, there is also four kinds of this function dealing with the distribution. So especially for this uniform distribution, we also have the unip, p unip, q unip, r unip function, as R already gives us as a function. So actually, this is just a introduction for or a brief explanation or a brief example for dealing with the uniform distribution. So as you already know, uniform distribution always need two parameter, hyperparameter, which is minimum value and the maximum value. So when we are dealing with a uniform distribution, like with D or P or Q or R function, we always have to set the hyperparameter, which is the minimum and maximum value of the uniform distribution, and also it also put our argument as our own end. So when you want to get the density value when our x value is 1, when our hyperparameter is 0 to 10, we can use the density function, which is 0.1. Actually, as you already know, the density of the uniform distribution is always same in their own support. So actually, we always get the same density uh, regardless of the x value. So it is natural that we always get the same value as the result of the d unit function if the minimum and maximum value is the same. So you can clarify the result by demonstrating the running this code and running this code. So as you can see, p unit also gives us the CDF value along with our Q value, which is a quantile. And as I already explained last week, rotation option means the direction. So actually, when you want to refer to the CDF value, it usually means the probability when our random variable x is less than or equal to our target value small x. So this is the meaning of the CDF value. So when you want to get the CDF value, we usually use this x input in p unit and p function here, and etc. And with the lower tail option as true. And as I already explained last week, lower tail option default value is always true, so you don't have to mention the lower tail option, even if you are dealing with a CTF value. So the lower tail option has to be true when you are dealing with a CTF value, because the meaning of the CTF value in the graph is kind of this value. So this is our target value small x, and we want to get the probability, which is the area of this field below the graph. So this is the left side of our target value. So we use this direction and also use the royalty option as true. So when you want to get the other direction, like this area, you have to set the royalty option as false, not true. And it is the same as the value, which is the 1 minus CDF value. So you have to always notice the relationship between the CDF value and the P function or the loyalty option simultaneously, so that you can solve any problem as problem request for us. So this is actually, we already know how to use the P function with the loyalty option in the last week, so there will be no difficulty in using this kind of function dealing with the uniform distribution. And Q function also gives us the quantity value, and R function gives us the random sample from the uniform distribution with this hyperparameter. So you can utilize these 4 kinds of function maybe in any kinds of situation. And this is nothing but just plotting the uniform distribution here. So this is just a visualizing thing. So which is not that important for us, maybe. And we can also get the mean and standard deviation of the uniform distribution after we generate the 1000 random sample from the uniform distribution and put all the random sample into the mean function or standard deviation function. We can also get the mean and standard deviation. So you can also check if this value is theoretically correct from this formula. Oh no, maybe yeah, in this formula. And our A is 0 and B is 10 in our situation. So we can see that it is almost same, which is 5 in our situation, and the result is about 4.88. However, you can see some difference from 2 values, but if we increase the random sample, the number of the random sample up to for example 100,000, you can see that the value becomes more closer to the real value, which is 5. So you can also see that as we increase the number of the random sample, we can also get more accurate value as we want. This is a kind of tip that we will deal with as a low of the large sample. So the next chapter is normal distribution. So normal distribution is actually one of the most important and one of the most famous distribution in the statistical world. So its PDF and density function is like this one. And as you already know, we need 2 hyperparameter, which is mu as mean and sigma squared, which is variance. So if we have our mean and standard deviation value, we can always get the density or percentile or quantile or random sample by using also the same kinds of functions, which is a denom, pnom, qnom, rnom function. So for example, when you want to get the density when our normal distribution has mean value as a 3 and standard deviation as 2, when our x is equal to 5, the density is about 0.1209 about. So we can always get the density or percentile like this. So and this is also the same thing, the plotting the normal distribution, which is not that important maybe in our class. So this is just for checking if we are really dealing with if we are dealing with a real normal distribution. So because the graph, the shape of the graph is more like bell shape with a uh, symmetric with the center as our mean, which is a 3, kind of. So we can see that, uh, yeah, we are in the situation in which we are dealing with a normal distribution, at least. So you can also see that our mean and standard deviation has the similar value as we set our argument as a mean as 3 and standard deviation as 3. Oh, yeah, as 2. I'm sorry. So this has to be 2 actually. But it doesn't affect the mean value, so the result became the same as the previous situation. So never mind. And so I think we also have to deal with some example in our class material PPT. So let's start with this 6th example. So actually this is the situation where we have to use the Pinon function because we are going to deal with the CDF function to solve these questions. So actually this is the same as the difference between two CDF function when x is less than or equal to 1.21 minus the probability when our x value is 0. So these two function can be the result from each CDF function. So we can use the CDF function here as a question number 1. So because we are dealing with a standard normal distribution, our mu is 0 and standard deviation is 1 as our hyperparameter in our Pinon function here for each function. And what we have to do is just setting the x value as our target. So we want to get the difference between the result from each Pinon function. One is the situation that our target x value is 1.21, and the other thing is the situation where our target value is 0. So we can see that it is about 0.38. And you can also see that for this value, we can also refer to the standard normal distribution table, which gives us the density result from the table. So when we use when z is 1.21, the density has to be this value, which is, you can see that the same as this result here in R programming. So yeah, and I will also deal with this question number 2. So actually, when you want to use the Pinon function with CDF value, we have to get the difference between, so we have to deduct the CDF value from 1, which is z is less than or equal to 1.21, I just deduct the result of the CDF value from 1 because I want to use the CDF function itself because the direction has to be this one. So in this situation, we can use the p norm function without setting any lower tail option like this one. Because lower tail option is always true as a default value, we don't have to mention the lower tail option when we are dealing it always the CDF function. So this is the reason why I just deduct the result of the p norm function from 1 here, which is the about 0.11. And if you are a little bit confused about the getting the difference between 1 and the result from the p norm function, you don't have to actually deduct the result from 1 if you set the lower tail option as false. Because if you set the lower tail option as false, let's say that this is the 1.21. When we want to get this area, this probability, it is the same as the p norm function with the lower tail option as false. Or if you want to use the lower tail option as true, as the default value, you have to deduct the value from 1. It is the difference between two options, between whether you are using the lower tail option true or not. So I just wanted to say that this code, this one, and the code below gives us the same result. The only difference is whether we are using the lower tail option as true or false. So I just recommend you always, you have to be actually always consistent with using the same function. So I recommend you not using lower tail option false. So I usually recommend you use the default value lower tail option as true, so that we don't have to mention about any lower tail option. So it means that we always can focus on the CDF function in any question. But if you feel more comfortable with this below option, actually it is on your own. So just do what you want. So that's it. And you can also refer to the answer in the other code because I prepared this answer for you. And there is also the question number 5 here, example number 5. So yeah, it gives us there's example number 5 and example number 34. And when our mean is 3 and standard deviation is 2, and we want to get the probability when our x random variable is between 2 and 5. And as you already know, it is the difference between two p norm function. The one is x is less than or equal to 5 minus the probability when our random variable x is less than or equal to 2. And our x follows the normal distribution with this mean and standard deviation value. This is what I prepared in this in this part. So I just get the difference between two result of the p norm function here with the same mean and standard deviation. So this can be the answer for the question number 1 actually. Yeah. And question number 2, it wants us to get the probability when x is more than 6. It is the same as 1 minus the probability when our random variable x is less than or equal to 6, which is the p norm function with the default value of the lower tail option So I use this code here for the answer. And question number 3 can be a little bit confusing because it wants us to get the how much muscle. So it needs us to get calculate the x value, not the probability. So uh, for getting this value, we have to know the target value. What you want to get is the target value when our random variable is more than or equal to our target value. The probability has to be 0.05. So which is this part, our target value here, which is a question box, and this probability has to be 0.05. For getting this our target value, which is small x, we can utilize the Q function. So with the rotation as force, because we are dealing with the right direction, the right part of our target value in our graph, we have to use the rotation as force. And our quantile value has to get the percentages of 0.05. I use the value here with the mean this part. So yeah, the answer has to be this one. Oh, sorry. I was dealing with this part. Yeah, I was confused because the mean and standard deviation was different from the previous situation, so I was a little bit confused, a little bit. Actually, we were dealing with example number 5 when our mean value is 3 and standard deviation is 2. So because we want to get the quantitative value of our normal distribution of the right side here, we have to set the rotation as force with this mean and standard deviation with the percentage value, this one. And the value is 6.28. So it means that it is 6.28 in our situation. That's it. And actually example number 34 is the same as the previous situation. So I think you can solve this question with my code without any difficulty in solving the question. So maybe I will skip this part now because all the process for solving the problem is the same as the previous question, previous example. So let's go to the next step. And the final chapter is the exponential distribution. So for exponential distribution, the density function is this one. And there's also the CDF function here, which gives us the probability when our random variable is less than or equal to our target value. And as you already know, and as you can already anticipate, there is also the D and P and Q and R function for exponential distribution, whose name is DXP and PEXP, QXP, and REXP. And because exponential distribution only needs the hyperparameter as the lambda, only one parameter, hyperparameter, what we have to put as a hyperparameter is the rate here as the lambda here. And this is our target value from each function. So I think there will be no difficulty in understanding how it works as the function dealing with the exponential distribution for u. And this code is also the nothing but just plotting the how the exponential distribution works. And I think this part has to be ignored because exponential distribution is only defined on the x whose value is positive value. So x has to be plotted, the graph has to be plotted from this part, not this part. So yeah, but never mind. It is not not that important for us. And you can also get the mean and standard deviation after generating the random sample from the EXP, from the exponential distribution with the hyperparameter rate. And there is also some example for dealing with the exponential distribution. So yeah, so let's say that f of 3 is equal to the CDF value when our exponential distribution x is less than or equal to 3, which is the p-exp function with the hyperparameter, with the royalty option as true, which is the default value. So this is the simple answer here. And for the example number 4.22, it says that our rate hyperparameter is 0.5, and it want to gives us the uh, it want us to get the probability when our x is more than 2, which is the same as 1 minus the probability when our exponential distribution x is less than or equal to 2. So this is why I use this code for getting the answer. So I deduct the result from the p-exp function from 1 here, which is the about 0.36. And as I repeatedly say, if you feel a little bit confused about getting the difference between two values, you can also use the percentile function, PXP function, with rotation as false. And as I say already, it gives us the same result from each other. And I usually recommend you use the upper part for being for us to be consistent with how to solve each problem. And for example number 4.21, actually it is easy actually because we are repeating the same process for solving each problem, although we are dealing with a various distribution. So I think our this is same as this one. So I use this function for the result. And yeah, this is also the same as when our x value is between 5 and 10, which is the same as, oh sorry, x, oh, capital X. This is the same as when our capital X random variable is less than or equal to 10 minus the probability when our x value is less than or equal to 5, which is same as this part here. So you can get the result like this one. So I think that there will be no difficulty in understanding all the material for today's lesson if you are familiar with using the same function from the last week. So because we are dealing with the same kinds of functions for dealing with each distribution, and the only difference is whether we are dealing with a continuous distribution or discrete random variables. So I think the most important thing is that we have to understand how the function works and just utilize each function adequately as the question request for us to us. So I think that's it for our today's lesson. And I will briefly summarize today's lesson lecture in Korean. 네, 그래서 고생하셨고요. 동영상 듣느라. 사실은 별로 어려울 게 없다고 생각하는 게 저번 주랑 같이 D 펑션, P 펑션, Q 펑션, R 펑션을 똑같이 쓰는 거예요. 대신 유니폼 디스트리뷰션인지 노멀 디스트리뷰션인지 아니면 익스포넨셜 디스트리뷰션인지에 따라 다르고 용법은 완전 똑같다는 거죠. 그러니까 하이퍼 파라미터만 잘 넣고 덴시티를 원하면 X에 넣으면 되고 CDF 밸류를 원하면 P에 넣으면 되고 쿼니티 밸류를 원하면 Q에 넣으면 되고 아니면 랜덤 샘플을 얻고 싶으면 R에 넣으면 되고 해서 그냥 문제가 원하는 대로 잘 구하시면 되는 거고 제가 마지막에 말했던 건 이런 걸 하나하나 뭐 예를 들어 굳이 외워야 되긴 하지만 굳이 막 하나하나 외운다기보단 사실 어떻게 보면 되게 쉬우니까요. 그냥 어떻게 쓰는지만 이해하고 문제가 어떤 걸 원하는지만 잘 파악을 해서 그거에 맞게 함수를 쓰기만 하면 됩니다. 그래서 큰 어려움은 없을 것 같다는 게 제 생각이고 언제든지 궁금한 것이 있으시면 저한테 메일을 주시면 금방금방 답을 해드리겠습니다. 어쨌든 고생하셨고요. So this is the end of the class for today's TST class and have a good day and see you later. Thank you.